Hello everybody. We continue our discussion on the divide and conquer method for algorithm design. And in our 6-step process, after generating the recursive definition, proving the correctness, creating the recurrence relations, and exploration of the properties, the core concept of divide and conquer comes from trying to balance the split. And this balancing of the split leads to the typical standard divide and conquer algorithm, while, as we discussed earlier, the overall process is an integrated process which involves all the techniques that are there to obtain the final algorithm. And today we shall again continue our discussion on the divide and conquer method and concentrate on at least 3 approaches which refer to how the split can be balanced in an appropriate manner to improve the complexity of the algorithm. From the given the original recursive definition, we then concentrate on how to optimize the balancing of the split. We recall the master theorem, which provides a very interesting guideline of balancing the split. And in the master theorem, we have this basic function where we are decomposing a problem into B subparts, and we would like to decompose, as we have seen, into equal subparts, and then we break it up into A such subproblems, and each subproblem is of the size of 1 by B of the original problem. And the values of A and B determine our function creation and the final complexity. And these are the 3 conditions that we have studied earlier of when Fn is of the order of n log A to the base B minus epsilon. In that case, it will be a very optimal function of n log A to the n to the power log A to the base B. On the other hand, if it is equal to n log A to the base B, then one log n term gets added to the complexity. However, if this is the case, that is, the value of this Fn, which is the critical recomposition and decomposition cost component that we have seen before, this Fn value, the A value, the B value and the Fn value dictate what we are. And this is the critical point of the relationship between A and B and N. So this critical relation gives us these 3 cases. We now come to the first problem under consideration. The first problem is that given 2 n-bit numbers, we would like to multiply them. And multiplication of 2 n-bit numbers, for example, if we have a number x is equal to 1 0 1 0 0 1, and if we have y is equal to 1 0 1 0 1 0, then if we try a longhand mechanism of multiplying, then we will first have 1 0 1 0 0 1 multiplied by 0. The next round is a shift, left shift will immediately multiply by 2 because we are doing binary. So we will do a left shift, and then this part will be multiplied by 1. Then we will do another left shift and multiply. So the first term is here, then the second term is multiplied by here. Now we are at the third term, and we will have 2 zeros but the third term is 0. The fourth term on the left is 1, so we will have the fifth term is again 0. And the last term is again 1. So there are three ones here, and obviously this number all becomes 0. So what we have to do is now we have to add these numbers down, and if we add only these three numbers which are remaining, we will get the final result of our choice. This is the final multiplication result. And if we apply a longhand result, then this method is very clearly an order n squared algorithm if we apply for multiplying to n bit numbers. So if this is an n bit number, then this method will give an order n squared multiplication. So let us now see how we can try a divide and conquer mechanism. So if we have to apply a divide and conquer mechanism, then we have x and we have y, and we split it, and we all know from the master theorem and our past experience that while we may look at various split operations, splitting in the middle is actually the optimal choice. So we will call this x1, this will call x2, we will call this y1, we will call this y2. So we have broken this up into two parts, with each of them are, this is an n by 2 bit portion. Similarly, this is an n by 2 bit portion. So now, what is the basic traditional way in which we can do the multiplication? If we try a recursive method, then the equation for multiplication by the recursive method will be 2 to the power n by 2. We can, as we have broken it up here, we can see that x can now be written like this. Y can be written as y1 into 2 to the power n by 2 plus y2, and x into y can be written as the product of x into y eventually becomes 2 to the power n x1 y1 plus 2 to the power n by 2 x1 y2 plus y1 x2, sorry, this will be x2 y1, which is the same thing, x2 y1 plus x2 y2. Now if we analyze the complexity of this, we see that we have got we have broken the problem into one multiplication here, 1, 1, 1. So we have broken it up into 4 multiplications, 1 here, 2 here, 3 here, and 4 here, and each of them is of size half. So our time complexity equation Tn becomes 4Tn by 2 plus this recomposition step, which is addition of n bit numbers, is order n. And if we apply this principle, then we will get an order n squared algorithm. By the master theorem, we will simply get an order n squared algorithm. So this will become order n squared, and we have not improved upon our method at all. But if we apply a slightly different twist and we change the order and the method in which we do our multiplication, then we will be able to get a better result. Let us see how we do that. So what we do is, this middle term x1 y2 plus x2 y1, we write a equal to, so we will now look at it in a different way, x1 y2 plus x2 y1. This a we will write down as x1 plus x2 into y1 plus y2 minus x1 y1 minus x2 y2. We have just taken out the factorization, and if we now rewrite xy as 2 to the power n x1 y1 plus 2 to the power n by 2 into a, the a that we have computed earlier, plus x2 y2, we now see that we have got it into only 3 multiplicative forms. There are only 3 multiplication forms. This is one type, this is the second type, and x1 y1, x2 y2, and this is the third multiplication is here. Within a, we have replaced the 2 multiplications of a by 1 multiplication, and the other multiplications of x1 y1 and x2 y2 are already multiplications which we will create, and by memoization we will reuse. So now our new equation becomes Tn equal to 3Tn by 2 plus order n. And by the master theorem, this becomes order n to the power log 3 to the base 2, which is the same as order So now we see that we have used the idea of optimizing the split in such a way that we are able to minimize the number of actual subproblems created. What we have done is we have created only 3 subproblems instead of 4, and by creating 3 subproblems and reusing the result by a simple trick, we have now been able to reduce the complexity. This is how we use this portion, the part A of the function fn, the part A of the function, and based on that part A of the function, we have now got an improved result. This is how we apply divide and conquer's basic technology of balancing the split to obtain an improved algorithm. So once we have an idea that we could do this for multiplying 2 n-bit numbers, we now move on to a slightly larger problem, and we apply the same, we see whether we can apply the same technique for matrix multiplication. So let us have a matrix A be an n by n matrix, and B be an n by n matrix. So we have 2 n by n matrices, and we want to multiply them. So if we apply the traditional divide and conquer technique, then we will have break this up into 4 parts, break B into 4 parts. Let us say this is A, B, C and D, and this is E, F, G and H. Then the final result of this matrix multiplication would be the following. we will have AE plus BG. Here we will have AF plus BH. Here we will have CE plus DG, and here we will have CF plus DH. And as you can see that there are 8 multiplications of size n by 2 by n by 2. So the complexity of this Tn is equal to 8 Tn by 2 plus order n squared, because here n squared is the way in which you have to multiply two n by n matrices and n by n matrix addition. To multiply them, you have to add. Here you have to add, here you have to add, here you have to add, here you have to add. So this addition of two n by n or n by 2 by n by 2 matrices will take order n squared time. And as we know, this follows the simple rule which we get from our master theorem, which is log 8 to the base 2, which is, this is order n cube. Now let us see whether we can balance the split and apply the same idea that we did for performing our multiplication of two n-bit numbers. So now Strassen's algorithm gave this unique idea of trying to reduce the number of multiplications. So it did a computation as follows. It calculated P1 is equal to A into F minus H. P2 is equal to A plus B into H. P3 is equal to C plus D into E. P4 is equal to D into G minus E. P5 is equal to A plus D into E plus H. P6 is equal to B minus D into G plus H. And P7 is equal to A minus C into E plus F. That means we now created 7 partial multiplications which we want to reuse to compute our final result. And by a simple trick of trying to do a manipulation of these numbers, Strassen very intelligently showed that this first term is P5 plus P4 minus P2 plus P6. The second term is P1 plus P2. The third term is P3 plus P4. And the fourth term is P1 plus P5 minus P3 minus P7. You can check it out yourselves. There can be other ways in which you can do it, but the interesting thing that was obtained by doing this was that now only 7 multiplications were required. And since 7 multiplications were required, the complexity, the time complexity of the problem now becomes 7 Tn by 2 plus order n squared. And again, by applying the master theorem, by reducing this by 1, we now got order n to the power log 7 to the base 2, because A is 7, B is 2. So by doing this, making this 7 and this 2, by doing this we get this equation, which is order n to the power 2.81 approximately, 2.81, which is much lower than order n cubed. So this is the second method by which we are able to utilize the power of reducing the split, the number of splits, so that the number of recompositions or the sub-problems that we have to solve recursively reduces, and that dramatically changes the complexity of the problem. We now move on to certain geometric problems. Since we have tackled many problems of other nature, and we have seen sorting, we have seen searching, we now come to a geometry problem. The first problem that we tackle in the geometric scale, that means we are given a set of two-dimensional points and we want to find the closest pair. That means the problem statement is given a set of n points in a 2D plane. Find the closest pair. The distance between these points can be measured by either the Euclidean distance or any other appropriate distance, Manhattan distance or something like that. So we need to find the closest pair of points. In general, the general case of the problem, the general version, is in some d dimension. Obviously, if this is the problem statement, there is a very easy way of order n squared comparison. So, straightforward method is an order n squared algorithm, where we compare everybody with everybody else, find the distance, etc. But our approach is to do a recursive algorithm, try to do the divide and conquer, and analyze the divide and conquer property. So we now write our algorithm. Our divide and conquer algorithm, let us call it closest pair given a set S, and let us say let S is equal to a set of x1, y1, x2, y2, and so on and so forth, xn, yn. Again, we use our traditional problem, split S into two disjoint non-empty subsets S1 and S2. Then we find out K1, which is the closest pair of S1. We find K2, which is the closest pair of S2. Now, diagrammatically, what have we done? If we look at a diagram, then we see that we had our points somewhere like this. We have split the set. For the time being, let us say we split it according to x-axis. We could have split it anyway, but for the time being, let us say we split it by some x-axis. We find the closest x1, k1, we find the closest k2. Now we have to compare the set of points in the set S1 and the set of points in the set S2 and get the result, knowing very well that we have already found K1 and K2. So let K equal to the minimum of K1, K2. We now have to find a combine algorithm which says this combine algorithm K3 is a combine of S1, S2, given that the minimum of the independently calculated subsets is this, and once we get K3, we return K3. So this is our algorithm. Our algorithm finds K1 from subset S1, K2 from subset S2, and then compares S1 and S2. Now, our trick is how do we compare S1 and S2. And on the other hand, if we look at the recursive equation, then the recursive equation that we get for this problem is as follows. We get Tn is equal to 2Tn by k. Sorry, we would break it up into two parts. So it will be Tn1 plus Tn2 plus some Fn. Based on our past experience, we have realized that breaking it up N1, N2 into equal parts is our best choice. So we immediately choose that we will break this up into like this, plus Fn. Now in order to break this up into two parts, or we have the option is 1, divide into two equal parts. The second option that we have at our disposal is that we divide randomly. As we have seen in quicksort, that if we divide randomly and check for average case. Now if we have to divide it into two equal parts, that means we have to find the median along x-axis. So we have to find the median, or we will divide it into two equal parts. Now this median finding algorithm can be done in two ways. A simple sorting would take us to an n log n algorithm, and the general, the most advanced median finding algorithm will do it in order n time. We have not studied the median finding algorithm yet, but as we have already discussed, there is a famous divide and conquer algorithm for median finding which can do this in order n time. So having decided that we will optimize this split into half-half, this split will be equal split. Having decided this, we have to now very carefully decide on the combine function. It is this critical combine function which will determine our complexity, because this split is order 1. These are our recursive steps. So the complexity of this Fn, which has been mentioned in this equation here, is what is going to determine our problem. So let us now analyze how we are going to do this combination. In order to analyze the combination, let us look at our 2D plane again. We know that along the x-axis we have divided it, and my points are at all these places. And among all these places, I have got maybe this as the minimum here and maybe this as the minimum here. And from this K1 and K2, I have now got a value K. So this is K1, this is K2 is the result of these two, K equal to minimum of K1 comma K2. So in order to now resolve what I have to do, the algorithmic steps are that I will create a strip of size K this side and size K this side, because the only elements that need to be compared amongst the two sides are the side of the elements in the side this side on the left of this cut and on the right of the cut. So I will have to compare, I will have to examine only those nodes, those points along this 2K strip on the boundaries. And these 2K strips on the boundaries, and I will find the set of points y, which consists of, I will strip S1 using K, union strip S2 with K. Then I will sort y. I will sort y by the, so let us do a little bit of renaming. Let us not call it y, it will get confused with y. So let us call this set of points, let us call this set of points something else. Let us call this set z. So we will sort z by the y-axis now. So how did we sort z by the y-axis? So now let this z equal to Q1, Q2 up to QR points. Now what do we need to do? We need to check for each Qi we need to check which points are there within K distance, and if so, find the minimum. And if there is such a pair of points, one on this side and one on that side, both the points cannot be on the same side, because that has already, from there already we have got K1 and K2. So since we have already got K1 and K2 from there, anything that has to be less has to be one from this side and one from other side. Now this gives us a very interesting computation, which means that does this comparison require every point in Z to be compared with many, or order n, other points in Z? This is my question. Do we now need to get an order n squared complexity there? The answer to this is no. The reason is that because k is the minimum of left side and right side, therefore there aren't points which are within distance of k either among the points on the left side or among the points on the right side. So there is a very interesting theorem which we shall now put to use, and that theorem says, so there is a very interesting theorem, and that theorem says the following. For each qi, we need to check at most 7 points. At least a constant number of points, which means this comes from a very neat geometric argument that between a point, from one point, we need to check only on the, if this is the point, then we need to check only between these two rectangles on the left and the right, which are of size k by k. And since we are sorted y and we are going only in one direction, we don't need to look at the bottom direction if we are looking at the top direction. We only need to look left and right. And since no other point can occur within such radiuses, so our situation is very interesting. Since no other point can occur within such radiuses of these 4 points, and you can draw circles of radius k around like this, you can show that at most, other than this, including this point, which is our point of reference, there will be total 8 points and only 7 points are there. The proof is very detailed and I am not going through the proof. But the core idea is that this comparison, which was expected to be an order n squared comparison, now becomes an order n comparison. So how does the algorithm now, how does the analysis of the algorithm come about now? The analysis of the algorithm, as we had just said, Tn is equal to 2Tn by 2 plus Fn. Now, suppose we sorted all the elements recursively to find the median, then case 1, we would require Fn will become order n log n. But if we do median case 2, if we do median finding, in order n time, and if Z is sorted, and this sorting, if we have to do every time, again there is an n log n component added to it, but this x-axis sorting and y-axis sorting is done once globally. If it is done once globally and reused at every recursive call, then all the sorting is done in order n time, and then this comparison, which was requiring only now 7 points, everything is in order n time. So the algorithm we see that Fn becomes order n. And this unique algorithm, when Fn becomes order n, then this becomes an order n log n algorithm. This is a non-trivial recomposition step which gives an order n log n algorithm. There is a more general theorem which says that for higher dimensions, that is for higher dimensions, in the case of higher dimensions or d dimensions, this algorithm then becomes order n log d minus 1 power n. So this is a very interesting problem where there is a non-trivial combination with a deep insight coming out from geometry that enables us to really solve the problem and find out the strip. From this strip find out whether there was anybody who was minimum. So by this combined part K3, so what we now have, this K3 Fn, this K3 becomes order n. This is what we have now achieved by an order n. If we did an order n log n algorithm, then we would have got something else. So because if we go back to the master theorem, then if we achieve an order n algorithm there, then we get order n log n. Otherwise, we would have got order n log squared n algorithm. Finally, we come to another very interesting problem, which is a very famous problem in 2D, 3D, ND geometry, is finding the convex hull. In 2 dimensions, suppose you are given a set of points. Colloquially speaking, given this set of points, the convex hull of these points is a polygon whose edges contain all the points, either on the edges or boundaries or on the vertices. This is how it is done. So in order to find a convex hull of a set of points, so suppose we are given a set of points and we want to find the convex hull of a set of points. So suppose we are given a set of points, we want to find the convex hull of this set of points. Then they apply a standard divide and conquer technique. They divide it into 2 parts. After having divided this into 2 parts, they find the convex hull of this individual components, and then apply an algorithm to check out and combine these components to find the convex hull. So again, the problem of convex hull of a set of points S again uses a split. It uses H1, which is split S into S1, S2. It finds convex hull S1, H2 is convex hull S2, and then H3 is combine H1, H2 and return H3. And it can be shown that this complexity, where this split can be done in order n time, Let us go back and see this algorithm. Here we had said we will split this into two empty non-disjoint sets. We could have done it in order n time, but now we will use the median. We have done the median finding to split it into two equal halves, and our combine is also order n. Earlier we had order 1 followed by order n log n, but now we are doing order n here. Here again we apply the same strategy. We apply median to split it into equal halves based on x-axis, and then we apply another order n algorithm to do this. So we will get Tn is equal to 2 Tn by 2 plus order n. And obviously there is a global sorting of the points both along x and y axis before the recursion globally, upfront before everything. So that takes another order n log n time. So the total complexity of the algorithm is n log n. So this is another famous problem, and you can work out the details of this algorithm on your own. So we now summarize that the divide and conquer approach is about balancing the split and ensuring the decomposition, recursion, and the recomposition steps. This yields my f1n, this yields my a and b, and this yields my f2n, and my complexity is Tn is equal to a Tn by b plus f1n plus f2n. I have not written the base conditions. And it is all about optimizing the ratio of A by B and the F1 and F2, or the max of F1n and F2n. And over this period of several lectures in the divide and conquer approach, we did searching, sorting, and then we did a plethora of matrix multiplication problems and certain geometry problems. There are several other classical problems which we have talked about, of which the median finding problem in order n time is an algorithm which we shall discuss later on in a subsequent class. The details of all this is available in the textbooks and the reference books mentioned. With this we come to an end of this lecture. If you have any questions, please feel free to ask.